extract certain features, and those features represent what's in the image. Now the difficulty is, how do we say what's in that image? That's not an easy thing. So for an example, what's in this image? How would you describe this image? If you can see it from where you are. You might say, some might say, well, it's just elephants. Or someone else might say, well, it's a national park. So there is some subjectivity, some context to the picture, so it's very difficult to describe. There's some semantic to the image. So anyway, that's a challenge in extracting features. Again, I don't want to go into how we extracted features at this stage. So once you extract features, you store the features as an index, and from this database you perform a similarity. So I have an image, my features are there, I have stored image, each one has its own features, and then I match and I retrieve the ones that matches closely to my query image. So our system includes lots of different features, and then these features that we extract from the image, we cluster them. When we cluster the features, the image gets segmented. So we extract features from each area and we send it to a clustering algorithm. The job of a clustering algorithm is to put similar things into one basket and other things in a different basket, in very simple terms. So what happens is, once we cluster features of this, we end up with an image like this. So as you can see, automatically we have been able to separate, let's say, the sky area, the background here, some sort of a mountainous area. This is all the grass, the undergrowth, and we have the elephant. So automatically the clustering algorithm has detected that there are, in this case, there are 5 different things. That's what it knows. It doesn't know what those 5 things are, but it knows there are 5 unique things. But the problem is there are different types of clustering algorithms, and each one will come up with different things. This is the challenge we face. So how do you know which clustering algorithm to use? Now, some clustering algorithms, you have to tell it how many unique clusters there should be. So if I tell you, okay, this is the image, there should be 5 unique clusters. So the algorithm finds, okay, these are the 5. Other clustering techniques, they work out. I don't have to tell them. The algorithm itself works out how many unique clusters are there. So you can see, based on the algorithm, this one class gave 5. K-means adaptively figured out there are 3. Another clustering algorithm, oh, hang on, there are 10. So this is the problem when we have automated system. But what we found out was, actually, it's very difficult to find the right one. But if we combine the knowledge of everything, we end up with a good solution. That's what we found. Because there was no one solution that fits every scenario. So this is where we combine different features, combine different clustering techniques, and we had a fusion-based system. So I'll show you some examples of the result. This is a database we use, again, a publicly available database. It has 10 different classes of images. Each class has 100 images, so in total 1,000 images. Now you can see the variety. So if I say, for example, buildings, if I send this image as building, I expect to retrieve these ones. But the problem is, see these ones, they're supposed to be buses, but there are buildings in them too. So if your system returns for this query image, this image, is it the right answer or is it the wrong answer? depends on what you're looking for, right? That's the difficulty when you're performing, when you're using content-based retrieval. That's semantic gap. But that's the challenge. So this is the database we used. And another example here. So this is beach, and then here we have mountains, and of course there are lakes. So are they two different things? If I ask for people, these are people images. But then what about people here? Should I retrieve them or should I not retrieve them? So anyway, you might not be able to see details. What you see here is, this is a query image, and out of a 999 other images in the database, even there are 1,000 in total, this is the top 20 retrieved images. So I give that image to system, and these are the top 20 images, based on one technique. You can see that there are, most of them are correct, but we have, this is not really relevant. And then there are two horses images, not relevant. Then there's one image here with a building. Then this is another technique, basically different features and different clustering algorithms. Again, majority are relevant to the query, but you also find mountains, elephant, horses, elephant. So this one has too many of irrelevant pictures, right? So if I look at this technique is better than this one. But what we did was we combined the two together, and what we got is these results. So we're down to simply 3 irrelevant images, but vast majority of the top 20 are the relevant images to our query. So this is the case where we use different features and different clustering techniques to segment them and then retrieve and we fuse the results. Of course, you can use this in so many different domains. Even if you want to use this in biology, you might have all kinds of images. You have a query image and you want your system to give you images similar to that, let's say, condition. This is work that I kind of just started early this year. So this is the same student who did her master's. Her master's was on smartphone identification, and now she's doing a PhD. I'm voluntarily supervising her PhD. She's working from Ghana in her own university. So they're looking for a supervisor, so I'm looking and I'll supervise her. It's about automatic detection and classification of diseases in cocoa crops. So these are cocoa crops. It's very important because cocoa is a huge cash crop in Ghana. But the problem is there are all kinds of diseases that affect cocoa production. So here, for example, frosty pod, black pod, different types of diseases. Now, because of this, farmers lose out a lot. Not every farmer is trained to identify diseases at an early stage. And if you don't identify the disease at an early stage, you can't intervene, you can't do anything about it, then you lose your crop. And sometimes they simply look at it and try to see if something is wrong. Or they have to get access to an extension officer, a trained officer who will go to the farm and look at it. They are not available all the time, and if they are, they're going to cost. So that's not really possible. So our work, what we're trying to do, we just started the work, is to use a low-cost camera, take a picture in both visible spectrum and infrared spectrum, and see if we can actually tell that crop is diseased or not. Simply on a low-cost device. Then the farmer can have a cheap phone, go around his cocoa plantation, take pictures and see are there any problems with the crop. So again, the steps are very similar in all the cases. Any image analysis classification system, the steps are quite similar. You have an image, you pre-process it because you want to clean things out, then you extract some features relevant to what you're looking for, then you use a classifier to come up with an answer. That's same in pretty much all cases. So in this work, what we're trying to do is use visible and near-infrared images because your cameras, actually phones, can use near-infrared images, can capture. Then we are thinking of using color, a combination of color and texture features, which we think will help us identify crop disease. Then what you're trying to do is, of course, we have a large pool of features. Now, not all of them are useful. We have to know out of this large pool of features, which ones are the most useful. So there are techniques that you can use to select the best out of this whole bunch. Okay. So we have to apply some feature selection. Then we will classify both visible and infrared separately, and we are thinking of fusing the two at a decision level. Say, yes, there is disease in this crop, this one doesn't, and if it is disease, what type of disease it is. That's what we're trying to achieve. But we just started with PhD, and she's just talking to her colleagues in the agriculture department to understand about cocoa plantations, about the crop, about the disease. And when she spoke to them, they said, oh, by the way, we want to know about soil samples also. If they have said, well, if you could classify soil samples, that'd be great. So that's another project, great. So yeah, this is at a very early stage. And again, this might be something very relevant to Sri Lanka as well. Some of you might be working on these things. I don't know. I'd be interested to talk to you. I have another thing, but I'll probably stop here. Should you want me to? It's a little bit. I'll leave out the technical stuff and give an overview of what we are doing. Is that okay? Right. So the last one I want to talk about is steganography. Using steganography to exchange biometric data. So steganography, for those who are familiar with, is communicating with someone, but without other people knowing that you are communicating something with a third party. Okay. So it's kind of like I send you a picture, just a normal picture. So anyone who sees that will see, oh, this is just a picture of your car. Fine, nothing to worry. But actually, hidden inside the picture is a message that nobody knows. Okay. So it's different to cryptography. In cryptography, we scramble the message and send it. So person in the middle knows that you have scrambled the message and you are communicating something important. In steganography, the person in the middle doesn't know that you are communicating something secret. They just think, oh, it's just a normal picture. And that's the difference between cryptography and steganography. So we have a normal message we want to send, and this is our secret. We embed the secret in the message, so the stego will look like that. And then the receiver can separate the two. So somebody, some modern sitting in the middle, listening to all your communications, only see your Twitter message, but doesn't see hidden there is some other stuff. Okay. So I'm going to skip all of these things. Okay, so our aim is to send biometric data hidden inside an image. The reason, so the question was, what's the application? One application is, imagine a situation where you have a security agent in another country looking for someone in that country. So they think that a person of interest is in that country. So Somebody goes there, an investigator, and the investigator now wants to send a picture of that person. So the investigator might have seen this person somewhere and takes a picture, right? I want to send this to my authorities to see, is this the right person? But the problem is, let's say in that country, you just can't send pictures in the open. Maybe in that country, everything is monitored, so you can't send a picture. If you send a picture in that country, they know, oh, there's an investigator from this other country, what are you doing in my country, kind of thing. You know? So that's one application. So I want to be able to send a picture to my authorities without alerting to people in the country. That's one application. Another application could be, let's say a journalist somewhere wants to take some pictures and send back to a different place. But the receiver wants to know that these pictures actually came from this journalist, not from somebody else. Because somebody else could have doctored the picture and sent it. So what you can do is the journalist can embed the journalist's biometric data in the picture. So the receiver, when they get the picture, can extract the biometric data and check, did this come from this genuine journalist? So those are two application scenarios. So this is a typical face recognition system. So we use local binary patterns to basically, this is a normal picture. We hide face by, again I don't want to go into details. Face, we take some features and then we hide these features in this normal image in very, very simple terms. If anybody wants details, I'm happy to send papers and stuff. Right. So at the receiving end, they only receive that picture. So nobody is worried about it. But from there, I can extract my face biometric data. But no one else can extract unless you know certain information. This is just to show that, right, even in steganography, there are ways to attack a steganography system. So just like in cryptography, people are trying to break cryptography system. Even in steganography, there are ways to look at the picture and see, is there something embedded here or not? So there are ways to do that as well. So basically, these figures are saying actually our technique is not easily detectable. So it will pass through most of the stega analysis techniques. Yeah, that's a particular application. This very last thing, this kind of future work is drones. So this is an area that I'm interested in working on. I'm talking to one or two people who uses drones for various applications. So I'm interested in analyzing drone-based video footages. So just imagine, this is a shore. So one of the things that I'm interested, or one of the things people are using drones for, is to inspect